consisting of a gaseous mixture of two or more components. The composition of the mixture can be described by giving the mass of the number of moles or each component present. Mole. A mole is an amount of a given substance numerically equal to its molecular weight. We have this formula that the number of moles is equal to the mass over the molecular weight of the components. Mass fractions. Mass fraction of component I is defined as the mass of its components divided by the sum of the masses of its components. A listing of the mass fractions of the components of a mixture is sometimes referred to as a gravimetric analysis, wherein the summation of the mass fraction of the components wherein I is equal to 1 up to j is equal to 1. The relative amounts of the components present in a mixture also can be described in terms of mole fractions. The mole fraction yi of component I is defined as yi equals ni over n, wherein ni is defined as Ni is the number of moles of a certain component, and N is equal to the total number of moles. A listing of the mole fractions of the components of a mixture may be called a molar analysis. An analysis of a mixture in terms of mole fractions is also called a volumetric analysis. Dividing each term of equation 12.5 by the total number of moles of mixture N and using equation 12.6, the apparent or average molecular weight of the mixture is defined as the ratio of the total mass of the mixture M to the total number of moles of mixtures N, wherein the molecular weight is equal to the mass over number of moles. We can also express the molecular weight by introducing equation 12.1, since yi of the component equals to. Finally, we have this. In order for us to fully understand and grasp these concepts, let us see and answer this example. Example number 1, converting mole fractions to mass fractions. And this is the problem. Let's go to the solution. We know that the molar analysis of the gaseous products of combustion of hydrocarbon fuel is given. Let's find the apparent molecular weight of the mixture and the composition in terms of mass fractions. Using equation 12.9 and molecular weights learned from the table A1 from the Moran-Shapiro thermodynamics book, we can solve the molecular weight by adding up all those values. We can now have the molecular weight, which is equal to 28.46 kilogram per kmol or 28.46 pound mole. Okay, for letter B, gravimetric analysis. In equation 12.1, 12.3, and 12.6, those are the key relations required to determine the composition in terms of mass fractions. Although the actual amount of the mixture is not known, the calculations can be based on any convenient amount. Let us base the solution on 1 kmol of mixture. Then with equation 12.6, the amount Ni of each component present in the kmol is numerically equal to the mole fraction, as listed in column 2 of the accompanying table. Column 3 of the table gives the respective molecular weights of the components. Column 4 of the table gives the mass Mi of each component in kg per kmol of mixture, obtained with equation 12.1 in the form of Mi equals the molecular weight and the number of moles of a certain component. The values of column 4 are obtained by multiplying each value of column. The values of column 4 are obtained by multiplying each value of column 2 by the corresponding value of column 3. The sum of the values in column 4 is the mass of the mixture, kilogram of mixture per kmol of mixture. The sum of the values in column 4 is the mass of the mixture, the kilogram of mixture per kmol of mixture. Note that this sum is just the apparent mixture molecular weight determined in part A. Finally, using equation 12.3, column 5 gives the mass fractions as a percentage. The values of column 5 are obtained by dividing the values of column 4 with a column for total and multiplying by 100. And that gives you the solution and the answers. For example, number 2, converting mass fractions to mole fractions. This is our problem. Okay, let's go for the solution. The gravimetric analysis of a gas mixture is known, and we must find the analysis of the mixture in terms of mole fractions and the apparent molecular weight of the mixture. Equations 12.1, 12.3, and 12.6 are the key relations required to determine the composition in terms of mole fractions. Although the actual amount of mixture is not known, the calculation can be based on any convenient amount. Let us base the solution on 100 kg. Then, with the equation 12.3, the amount Mi of each component present in kilogram is equal to the mass fraction multiplied by 100 kg. Values are listed in column 2 of the accompanying table. Column 3 of the table gives the respective molecular weights of the components. Column 4 of the table gives the amount Ni of each component in kmol per 100 kg of mixture. Obtained using equation 12.1, the values of column 4 are obtained by dividing each value of column 2 by the corresponding value of column 3. The sum of the values of column 4 is the total amount of mixture in kmol per 100 kg of mixture. Finally, using equation 12.6, column 5 gives the mole fractions as a percentage. The values of column 5 are obtained by dividing the values of column 4 by the column 4 total and multiplying by 100. And for B, and for the apparent molecular weight of the mixture, it can be found by using equation 12.9. In the calculated mole fractions, the value can be determined alternatively by using the column 4, total giving the total amount of mixture in kmol per 100 kg of mixture. Thus, with equation 12.8, the molecular weight is equal to the mass over the number of moles. 100 kg divided by 7.82 kmol is equal to 12.79 kg per kmol or 12.79 pound mole.
For the Dalton's law states that the total pressure of a mixture of gases is equal to the sum of the partial pressure, while partial pressure is the force that each individual gas would exert by itself at the same volume as the same mixture and the same temperature. The partial pressure can be evaluated as, and when divided by the gas law, we get. Then, for the sum of the mole fraction, for example, a bottle of soda, or we call as carbonated soft drinks, the gas above it is almost pure carbon dioxide, having a pressure much higher than the atmospheric pressure. If we open the bottle, some of the gas will escape, giving us the sound of hiss. Then, the pressure above the liquid now is lower, and some of the dissolved carbon will also escape in a form of bubble. And through time, if left unattended, that drink will go flat since the carbon will reach its equilibrium with the environment. On the other hand, the Magat's law states that the volume that each gas of a mixture would take up if separated add up to the total combined volume. Amagat's law assumes that the volumes of the component gases are additive. The interactions of the different gases are the same as the average interactions of the components. When Amagat's law is valid and the gas mixture is made of ideal gases, we get this equation, where P is the pressure of the gas mixture, and then the VI is the volume of the I component of the gas mixture, and then the V is the total volume of the gas mixture, and I is the amount of substance of I component of the gas mixture, where N is the total amount of substance of gas mixture, R is the ideal or universal gas constant, T is the absolute temperature of the gas mixture in Kelvin, and the Yi is equals to Ni over N, and is the mole fraction of the I component of the gas mixture.
So hi, we are in question number 3. So since the gas in a mixture have different properties, so the question here is, how do we evaluate the internal energy, the enthalpy, the entropy, and the specific heat of a gas mixture? So to apply the conservation of energy to a system involving an ideal gas, a mixture requires evaluation of the internal energy, enthalpy, or the specific heats of the mixture at various states. So for evaluation or evaluating the internal energy and the enthalpy, we consider a closed system considering of an ideal gas mixture. So there is extensive properties of the mixture, such as the internal energy, the enthalpy, and the entropy, and it can be found by adding the contribution of its component at the condition at which the component exists in the mixture. Let us apply this model to the internal energy and the enthalpy. Since the internal energy and the enthalpy of the ideal gases are functions of temperature only, the values of these properties for its component present in the mixture are determined by the mixture temperature alone, and accordingly, here is the equation for the enthalpy and the internal energy, where the enthalpy or the U sub I and the H sub I are the internal energy and the enthalpy respectively of component evaluated at the mixture temperature. So it can be written or rewritten on the molar mass basis as this equation above, where U and H are the specific internal and enthalpy of the mixture, promote of mixture, and U sub I and H sub I are the specific internal energy and the enthalpy of component I per mole of I, then dividing by the total number of the moles of mixture. U gives expression for the specific internal energy and the enthalpy of the mixture per mole of mixture respectively. So here's the equation. So it's of the molar internal energy in the enthalpy terms is evaluated at the mixture temperature only. So now we are evaluating the specific heat for the volume and the pressure. So these are the expression for the specific heat, C sub V and C sub B of the mixture of the molar basis. So here's the equation. So that is the mixture specific heat. Cp and Cv are the mole fraction average of the respective component specific heats. The specific heat ratio for the mixture is K equal to C sub B divided by C sub B. So for the evaluation of entropy, so evaluating entropy, the entropy of a mixture can be found as for internal and enthalpy by adding the contribution of its component at the condition of its component at the condition at which the component exists in the mixture. And the entropy of an ideal gas depends on two properties, not on the temperature alone. So for internal energy and enthalpy, accordingly for the mixture. So here's the equation for the evaluating of entropy, where S sub I is the entropy of component I evaluated at the mixture temperature T, and partial pressure were written in T sub I, or at the temperature T and total volume. So can be written on a molar basis as this equation. So where hyphenated in the above, S is entropy of the mixture per mole of mixture, and E sub I is the entropy of component I per mole of I, dividing by the total number for the entropy or total of moles of mixture, and give us expression for the entropy of the mixture per mole of mixture. So here's the equation. The specific entropies S sub J are evaluated at the mixture P and the partial pressure P sub I. So that's the way of how we evaluate the internal energy, the enthalpy, the entropy, and the specific heats.
Good day everyone. For today's video, we'll be analyzing systems involving mixtures. So for mixture processes at constant composition. So looking at the figure, we have here this from state 1 to state 2, which is concerned with the case of ideal gas mixture undergoing processes during which the composition remains constant. So it is labeled with internal energy, enthalpy, and entropy for state 1 and state 2. So if we are going to look for the change in the internal energy and the enthalpy of the mixture during the process, we are given by internal energy of state 2 minus the internal energy of state 1. Same goes for enthalpy, H2 minus H1. So for the change in internal energy and enthalpy of the mixture per mole of mixture result, it is given by this equation. So for entropy, it is also dependent upon pressure changes. Therefore, it is S2 minus S1. And so by using the ideal gas table, we can evaluate the entropy change. Assuming the constant specific heat, we can determine the entropy change of the mixture and the components of the mixture, which is represented by delta S dash. So we have here a sample problem. A mixture of 2 kilograms of hydrogen and 4 kilograms of nitrogen is compressed in a piston cylinder assembly in a polytropic process for which N is equals to 1.2. The temperature increases from 22 to 150 degrees Celsius. Using constant value for specific heats, determine the heat transfer and the entropy change. So by listing the given, we have 2 kilograms of hydrogen and it has a molecular weight of 2.016 and specific heat of 10.183 kilojoules per kilogram that Kelvin. And we have 4 kilograms of nitrogen, which has a molecular weight of 28.018 and a specific heat of 0.743 kilojoules per kilogram that Kelvin. And we have N is equals to 1.2, T1 is equals to 22 degrees Celsius, and T2 is equals to 150 degrees Celsius. So step 1, find the moles of each component and the mixture's molecular weight. So by following the pattern for this solution, we'll have the molecular weight of the hydrogen and the nitrogen as 5.2. Step 2, evaluate work for polytropic process. And by substituting the values, we'll have work is equals to negative 6,139.569. And step 3, evaluating change in internal energy. And again, by substituting it with its respective values, we'll have the change in internal energy as the 2,987.264. And so the heat transfer is equals to the change in internal energy plus the work done during the polytropic process. So therefore, the heat transfer during the process is negative 3,152.305 kilojoules. And for B, we are looking for the entropy change. So let us first determine the specific heat of the mixtures. Therefore, the CV of the mixture is equals to the total mass of H2 times the CV of H2 plus the total mass of N2 times the CV of N2. Again, by substituting its respective values, we'll have CV is equals to 3.89 kilojoules per kilogram that Kelvin. And now we are evaluating the mixture CV, which is obtained by CV times the total molecular weight. Therefore, the mixture CV is equals to 3.89 times 5.2 which is equals to 20.228 kilojoules per kilomole dot Kelvin. And so by using this equation, we can obtain the entropy of mixture per mole, and by substituting its respective values, we'll have negative 1.46 kilojoules per kilomole dot Kelvin. And since we're looking for the entropy change, we can obtain it by dividing entropy of mixture per mole divided by the total molecular weight. And so we'll have negative 0.281 kilojoules per kilogram dot Kelvin. And lastly, we'll have to multiply the total mass and the entropy change that we have to obtain. Therefore, we'll have the entropy change of negative 1.686 kilojoules per Kelvin.
Minor losses. The fluid in a typical piping system passes through various fittings, valves, bends, elbows, teeth, inlets, exits, enlargements, and contractions in addition to the pipes. These components interrupt the smooth flow of the fluid and cause additional losses because of the flow separation and mixing they induce. Minor losses are usually expressed in terms of the loss coefficient KL, which is also called the resistance coefficient. When the loss coefficient for a component is available, the head loss for that component is determined from this equation. If the entire piping system being analyzed has a constant diameter, which is the total head loss, the D is constant. Values of K for different kinds of fittings. K is the sum of all of the loss coefficients in the length of pipe, each contributing to the overall head loss, which is the basis of efficiency of the pipeline. The head loss coefficient measure of the efficiency of the inlet to smoothly transition from the upstream channel into the culvert, meaning the less value of KL, the pipeline is efficient. So based on the figure, well-rounded, which is fitting to the pipeline, is more efficient inlet pipe. We can also conclude that the geometry of the component affects value of KL.
Okay, number 6. A. What is a humidity ratio? The specific humidity or humidity ratio of an air sample is the ratio of the weight of water vapor contained in the sample compared to the weight of the dry air in the same sample. Or, humidity ratio omega is equal to mv over ma. It can also be expressed in terms of partial pressure and molecular weights and will be simplified with this formula. With Pa is equal to P minus Pv and the ratio mv over ma is 0.622, approximately, the formula may now be written as with this. Letter B. Relative humidity. The amount of water vapor present in an air expressed as a percentage of the amount needed for saturation at the same temperature, or relative humidity phi YV over YV saturated. Since PV is equal to YVP and PG is equal to YV saturated P, the relative humidity can now be expressed with this formula. C. Mixture enthalpy. The enthalpy of a given moist air sample is H is equal to MAHA plus MVHB. Dividing by M will give us the mixture enthalpy per mixture enthalpy unit mass of dry air. D. Mixture entropy. Meanwhile, the mixture entropy on a mass basis is S is equal to M1S1 plus M2S2. But in a moist air, mixture entropy contributes the water vapor and the dry air. E. Dew point temperature. Dew point temperature is defined as the temperature to which the air would have to cool in order to reach saturation. Considering a sample of a moist air on closed system, cooled at constant pressure, the property diagram on the figure locates the state of the water vapor. The partial pressure remains constant while it cools at constant PV from state 1 to D is called the dew point. Meanwhile, the temperature corresponding to this is the dew point temperature. Letter F. Lastly, wet bulb and dry bulb temperature. The wet bulb temperature is read from a wet bulb thermometer, which is an ordinary liquid in-gas thermometer whose bulb is enclosed by a wick moistened with water. The term dry bulb temperature refers simply to the temperature that would be measured by a thermometer placed in the mixture. Often, a wet bulb thermometer is mounted together with a dry bulb thermometer to form an instrument called psychrometer. Wet bulb temperature is the lowest temperature to which air can be cooled by the evaporation of water into the air at a constant pressure. The dry bulb temperature is the ambient temperature. The difference between these two temperatures is a measure of the humidity of the air. That is all. Thank you.
Illustrate the process how to use a psychrometric chart. Present a sample diagram and give example. First, what is psychrometric chart? It displays the properties of air, dry bulb temperature or vertical lines, wet bulb temperature, lines sloping gently downward to the right, dew point temperature, horizontal lines, and relative humidity or the curves on the chart. How do you read psychrometric chart? First, you need to locate the dry bulb temperature along the bottom axis and the associated vertical line for each temperature. This scale will be in degrees Fahrenheit or degrees Celsius. Step 2. Locate the humidity ratio. Along the right vertical axis, humidity ratio units are grains of moisture per round of dry air or grams of moisture per kilogram of dry air. The term humidity ratio is sometimes used interchangeable with the term mixing ratio. Step 3. Locate the leftmost curved line. This is the saturation curve where the relative humidity is 100%. Other properties of the saturation curve include dew point temperature equals dry bulb temperature, wet bulb temperature equals dry bulb temperature, partial pressure of water vapor equals saturation vapor pressure. Step 4. Locate the interior curve lines. Each of the lines represents a certain level of relative humidity in percent. Step 5. On the right side of the chart, locate the vertical line labeled dew point. Dew point is expressed as a temperature. The dew point lines traverse the chart as horizontal lines. What this tells you is that dew point does not change as the dry bulb temperature varies. Step 6. On the other side of the vertical line, where you located dew point is the scale for vapor pressure expressed in inches of mercury or millibars. Vapor pressure lines also traverse the chart as horizontal lines. Look at the information on all sides of the chart that is on the most extreme edge. These scales represent enthalpy expressed in BTU per round of dry air. If you take a ruler, you could match the scales diagonally across the chart. Step 8. Look closely and find a second set of diagonal lines representing wet bulb temperature, expressed as degrees Fahrenheit or degrees Celsius. Although the wet bulb lines are close to the enthalpy lines, they are not actually parallel to each other.
Explain the process in analyzing air conditioning process, which includes mass, energy balance, dehumidification, humidification, and adiabatic mixing of two moist air streams.
So, let's start with this figure. It is the system for conditioning moist air. It has two inlet, single exit control volume at steady state. From the figure, the amount of dry air and water vapor contained within the control volume cannot vary. Thus, for each component, it is necessary for the total incoming and outgoing mass flow rates to be equal for dry air and for water. The mass flow rate of the water vapor can be expressed conveniently in terms of humidity, which is shown in this equation. So for the energy balance is the energy balance equation for for conditioning moist air. So, we will proceed in the humidification and humidification process in air conditioning. So, air conditioning is a must for surviving hot summer. During the summer, your indoor humidity level should be somewhere between 35 and 65%. Lower than 35% and you'll notice dry skin, irritated eyes, and sinuses. The first process in containing the level of humidity is through dehumidification. Literally means pulling out or removing the moisture or humidity from the air. In air conditioning system, it is obtained by increasing the total pressure or compressing the air. The figure shows the equipment schematic and the psychrometric chart representation for dehumidification. The formula shows the mass flow rate in dry air and water, and also the mass flow rate of the condensate. So by applying the humidity ratio, we can also obtain the mass flow rate per unit mass of dry air passing through the device. The equation shows the energy rate balance for dehumidification. Next, let's go to humidification process, or to increase the humidity in the air. It is often necessary to increase the moisture content of the air circulated through occupied spaces. One way to accomplish this is to inject steam. Alternatively, liquid water can be sprayed into the air. The figure shows the control volume of humidification and the psychrometric figure of the steam injected and the liquid injected humidification process. Next is in adiabatic mixing of two moist air streams. A common process in air conditioning system is the mixing of moist air streams. The objective of such process is to fix the flow rate and state of the exiting stream for specified flow rates and states of each of two inlet streams. So the figure shows the adiabatic mixing of two moist air streams. The A is for the equipment representation and for B is the psychrometric chart representation.